Complete instruction execution cycle. So from before, we know that there are 4 different types of basic operations. First one is fetching information from memory to CPU. Second one is storing information to CPU register to memory. Third one is transferring of data between CPU registers. And finally, the fourth one is performing arithmetic or logic operation and storing the result in CPU registers. Now, to execute a complete instruction, we need to take help of these basic operations. And we need to execute these operations in some particular order. So let us take an example. We want to add the contents of memory location num to the contents of register R1, and finally we want to store the result in register R1. So for simplicity, let us assume that the address num is given explicitly in the address field of the instruction. That is, in this instruction, direct addressing mode is used. Now, to execute this instruction, we need to follow some actions. What are those actions? First one is fetching the instruction, second is fetching the first operand, third is performing the addition, and fourth one is loading the result into R1. So in order to execute this instruction, we have to follow some steps. Let us look at the first step. PC out, MAR in, read, clear Y, set carry into ALU, add, Z in. So what does this mean? I'll tell you. You see, in the first step, the instruction fetch operation is initiated by loading the contents of the PC, that is the program counter, into the MAR, which is the memory address register. To perform this task, first of all, the contents of the program counter have to be brought to internal bus and then it is loaded to MAR. So to perform this task, the control unit has to generate the PC out signal and MAR in signal. After issuing the read signal, CPU has to wait for some time to get the MFC signal. What is the MFC signal? It is the memory function complete. It is a signal that tells the CPU that the current operation involving the memory is complete. During that time, the program counter is updated by 1 through the use of the ALU. This is accomplished by setting one of the inputs to the ALU, which is the register Y in this case, to 0. And the other input is available in the bus, which is the current value of PC. At the same time, the carry in to the ALU is set to 1 and an add operation is specified. Now let us move on to step 2, that is Z out, PC in, wait for MFC. Now in step 2, the updated value is moved from register Z back into the PC. Step 2 is initiated immediately after issuing the memory read request without waiting for completion of memory function. Now this is possible because step 2 does not use the memory bus and its execution does not depend on the memory read operation. So that is it for step 2. Now let us move on to step 3. MDR out, IR in. Step 3 has been delayed until the MFC is received. Once MFC is received, the word fetched from the memory is transferred to IR. What is IR? It is the instruction register. Step 1 through step 3 constitute the instruction fetch phase of the control sequence. So that is the instruction fetch portion. Now from the next step onwards, we will move on to the instruction execution phase. As soon as the IR is loaded with instruction, the instruction decoding circuits interprets its contents. This enables the control circuitry to choose the appropriate signals for the remainder of the control sequence, that is step 4 to step 8, which we refer to as the execution phase. To design the control sequence of execution phase, it is needed to have the knowledge of the internal structure and instruction format of the PU, that is the processing unit. Secondly, the length of instruction phase is different for different instruction. In this example, we have assumed the following instruction format. As you can see in the PPT, we have the opcode, that is the operation code. We have M, memory address for source, and R, register address for source or destination. Now let us look at step 5, which is R1 out, Y in, and wait for MFC. You see, the destination field of IR, which contains the address of register R1, is used to transfer the contents of register R1 to register Y, and then wait for memory function complete. When the read operation is completed, the memory operand is available in MDR. MDR means memory data register. Then we move on to step 6, which is MDR out, add, and Z in. In this step, the result of addition operation is performed. Then in step 7, we see Z out and R1 in. The result of addition operation is transferred from temporary register Z to the destination register R1 in this step. Remember, we wanted to store the result in the R1 register itself. Finally, we are on to the last step, that is step 8. We can see that it is written end. This means that we are at the end of the execution of the instruction, and it is done so by generating an end signal. This indicates completion of execution of the current instruction and causes a new fetch cycle to be started by going back to step 1. So we have finally come to an end to our video, but before that, I just want to say thank you all for watching and listening to this video. This is a group assignment of the subject Computer Organization and Architecture, guided by our Professor Smita ma'am.